We are continuing to look at a number of data structures that are very popular that you need to know before you graduate. And the one we're going to start with today is heaps. So heaps are somewhat related to priority queues, which you have learned early on in your career. Remember that a priority queue is a special type of a queue which gives priority to every element in the queue. Consequently, when you remove an element from the queue, you are actually removing the highest priority now. After you've inserted a number of them, they get sorted internally and by priority, and when you take an element out, you always remove the highest priority. Okay, this has lots and lots of applications, including, for example, routers at your home, including all kind of network appliances, and also high-level applications like auctions and stock market and so on would use typically priority queues. So I want you to remember that because we gotta do something that is quite related. Now we could also, by the way, use priority queues to do sorting. Okay, so you insert them in a priority queue, they get in order, and then you take them out one by one, and here you go, you got the elements sorted. Okay, now, so I'm not going to review this code snippet. This is something you have seen many years back in your early computer science education, but I'm just going to highlight the fact that we can use priority queue in sorting. Let's move now to the new topic, heaps, one of the most popular data structures. In fact, it's a shame that you didn't learn this early on in your computer science education. Usually students who do ACM problems would get exposed to this much earlier, but if you haven't been doing ACM problems, this is probably your first time hearing about heaps. So what is a heap? A heap is a binary tree. Wow, okay, so it is like a binary search tree. So this is a binary tree. It respects this invariant that at most you could have 2 children per node. Okay? However, a heap satisfies another invariant, and the invariant is like this. For every internal node v other than the root, the key at the v is greater than or equal the key of the parent of v. Okay? What does that mean? Look at the right side, you see a heap. The key in any node is greater than or equal the parent of that node. Okay? So 5 is greater than 2, 6 is greater than 2, 9 is greater than 5, 7 is greater than 5. So this is not a binary search tree, obviously, it's something else. The values are listed so that the node is inserted is always going to be bigger than its parent. This is at least one way to think of heaps. Okay? Or we could reverse it. So we will talk later on about a max heap and a min heap. But if we just apply this idea that every node is bigger than its parent, the smallest node is going to be at the top. And this is what you see in the image in the right side. The smallest value is at the top. So later on we will call this a special name, we will call it min heap. Now, why this is interesting, we will see. So this is a different way to organize a binary tree compared to the binary search tree. Remember, binary search trees, the invariant was all the nodes to the left is less than all the nodes to the right is greater than. Here we're saying one way to organize it is all the nodes at any level is bigger than their parent. Or you could reverse it, all the nodes at any level is smaller than their parents. Okay? So we will see where that will take us. Okay? Now, another thing you also need to notice here is that a heap is filled, if you would like, left to right. So the last node to be filled is the 7. In other words, we are trying, we will not always be there, but we are trying to be working with a complete tree where there is a value in every possible slot. Obviously, this is not complete because 6 has no left or right child, but if it does, then the tree will be complete. There will be all nodes wherever we can find a node, wherever we can insert a node. Okay? but the general direction here, or the general behavior is we're going to fill the tree from left to right. So we filled level 1, we filled level 2, now we're filling level 3 if you'd like. Or if you think of the root as level 0, then level 1 is going to be the one that has the 5 and the 6, and then we start filling level 2, which is having 9 to 7, and the next time we insert, it's going to be the left child of 6 and then the right child of 6. So it's filled from left to right. Now, what about the height of the heap? Okay. Now, I just already described this. Since we are filling in the heap from left to right, one level at a time, what that means is we are always going to be working with log n height, because we are actually opting here for as much as we can to get a complete tree. And a complete binary tree means there is a node at every location possible, with the except of the leaf level. Okay, and that's what you see with the illustration at the bottom. We fill depth 0, and then we fill depth 1, and then we fill depth 2, and then we fill depth 3, all the way till depth h. Okay, so this is an important property that actually will make us do certain things later on that are very, very interesting as the details will come along. Okay, this is called the complete binary tree property. Okay, that we're trying to complete the binary tree from left to right, all the way, all the time. Now, why did I discuss priority queues early on? We can use a heap to implement a priority queue. Okay, since one way to build a heap is to put the smallest value at the root and everything else below it is bigger, and if our priority is actually to get the smallest value out first, we can implement a priority queue using a heap. So the next time we say, okay, get us the next value, we're going to get the root. And after the root, we get the 5, and after the 5, we get the 6, and after the 6, we get the 7, and then the 9, and so on. Okay. Now, we will see how all of that is going to be done, but this is the point. Heaps are very related to priority queues. In fact, the most popular way to implement a priority queue is using heaps, as we will see. Okay. How do we insert into a heap? Remember, we are after a complete tree. So what we're going to do is we're going to insert the new element at the leaf level in the next immediate available slot from left to right, which means it's going to be the left child of 6. Let's say, for example, we're inserting a 1. And what we're going to do next is that we are going to do a process called upheap, or upheaping, or bubbling up, where we take the value that we inserted, if we need to, and propagate it upward all the way until the heap order property is respected. So if this is a min heap, which means the smallest value is at the top, and I'm inserting a 1, I need to bubble it up as long as the parent is greater than the 1, the parent is greater than the child, I will bubble up the child, or I will upheap the child. So this is what we have here. We inserted the 1 in the leftmost location we could identify at the lowest level, which is going to be the left of 6. And then, since the invariant here is that the child should be greater than or equal to the parent, and since this is violated because 1 is less than the parent, I upheap 1 by exchanging its location with 6, and then I check the parent of 1, which is 2, and again that will result in a violation of the heap property, so I change the 1 with the 2. So what is going on here, after every insertion, we are upheaping or promoting, bubbling up the value all the way perhaps till the root, so that the smallest value is always at the root. Okay? And that will always happen with every insertion. So if I insert a 0 later on, it will come to the right of 2. I'm referring to the illustration on the right side. And then I will compare the 2 with the 0, so I will bring the 2 down and the 0 up, and then when I compare the 0 with the 1, I'll bring the 1 up, down, and the 0 up. Okay? What if I inserted a 3? Well, a 3 will go to the right of 2. And when I do the comparison with the parent, I'm always comparing with the parent. Well, the parent is less than the child, so I'm happy, I'll keep it there. The next thing we're going to look at is the removal from the heap. Now, we usually use heaps because we would like to access the smallest element or the largest element as fast as possible. Now, the smallest element, in the case that in front of us, will exist at the root if this is a min heap, and consequently we would like to eliminate the root. But that creates a problem because that will split our heap into 2 subtrees. So what we're going to do is the following. We're going to go and pick the last element to the left in the last level and put it instead of the minimum value that we are extracting from the heap. So I will take the 7 and put it instead of the 2. And then what I'm going to do afterwards is the following, because now this violates the heap order property and I cannot leave it like that. So what I'm going to do is I'm going to do something called down heap, where I grab the value that I have put at the root level, in this case the 7, and I push it downward by comparing it with its children, swapping the smallest of the 2 children in its place and bringing it down, and I keep doing that until the heap order property is respected, okay, or is maintained back to its original state, okay, because this is an invariant that we will always have to hold true. So I will compare the 7 and the 5. I will put the 7 up and exchange its location with the 5, which means put down heaping or pushing down the 7, and I keep doing that until I am done, okay. Again, in the min heap way of thinking, the smaller value has to be at the parent and the children are greater than or equal to the parent, okay. So you know, it is okay to have the 9 being the child of the 7, so I will stop there. And this will be always our strategy when we delete the minimum. We bring the last node at the bottom level from the left, you know, so basically the last node in our tree, if you'd like to think of it that way, and we put it at the root and then we down heap it. Now, there is actually a sorting technique that you could use with the heap, okay. You could do heap sort in n log n, and this is really nice. So this is another n log n algorithm. You have seen in this course merge sort and you have seen quick sort. Heap sort also is an n log n. Now, okay, how would you do a heap sort? Well, it's easy. You put in all the numbers in the heap and then extract all of them, okay. Now, when you're doing that, it turned out to be an n log n exercise. Again, why? Because this is based on comparisons. We already covered, you know, this notion of comparison-based sorting, and this is a lower bound on comparisons. The question is, you know, is it n log n or n squared? And the answer is it's actually n log n, because you're doing comparisons in a tree, so you'll go left and right when you're inserting and removing the values, and consequently you're really talking about log n height of the tree, and you're doing the processing on that tree of log n as many elements as there are, which is n, and you're doing every one of the n in log, takes log n effort to insert and delete, so it's n log n. Now, the nice thing about heaps, and that's why they're very popular, we don't actually implement them as a tree, okay. The explanation at the beginning makes perfect sense. It's a tree, okay. In reality, it's not implemented as a tree. It's implemented in an array. So the question is, why an array? Typically, trees are not easily represented as an array, because the good thing about array is that the cells are adjacent to each other. And the nice thing also about arrays is that they're super fast to work with, because you don't have references, you know, you don't have objects, you just have an array of values, okay. So they're very simple, and that means any work you do on them will be using a simple for loop, and consequently it's going to be generally faster. But the question is, why arrays? And here is why. When we are building the heap, we're always making sure that we fill in one level before going to the next level. So always the empty slot will appear at the end of the tree towards the right. So because of that, we can take the elements in the heap and organize it in the array in a way that preserves the order. How can we preserve the order? Well, we were going to use a very simple formula. If I would like to pick or to find the children of some value at location I, the children are going to be at 2i and 2i plus 1. So as you see here, the 2 which was at the root will go into cell 1 in the array. We will always keep cell 0 empty in order for this to work. The children of 2 is 5 and 6. We will actually put them at 2i, which is 2 by 1 is 2, and 2i plus 1, which is 3. We will put 5 and 6 in cells 2 and 3 according to our formula 2i and 2i plus 1, where I is the index of the parent. And then we'll apply the same approach to the rest. The children of 5 are 9 and 7. 5 is in location or in index 2. So its children is going to be in 2i, which is 4, and 2i plus 1, which is 5. And that's what you see, 9 and 7 went into 4 and 5. Okay? Why does this work? Because the heap is, we're always trying to make it as complete as possible. So we're filling it level by level, left to right. So there's no gaps inside the heap tree. The gaps are always at the bottom right. And that will mean, or at the bottom leaf level. What that means is the empty space in the heap will always be at the far right end of the array. So all the values will exist adjacent to each other at the left side of the array, starting from index 1, and the empty space are way at the back. So we'll never actually run into a situation where we have empty slots in the middle. What's also interesting is that this way we will get access to the smallest value in O of 1 from an array, which is going to be at location 1, at a cell index 1. Okay? And what we're going to do is, once we extract the minimum, we will just keep a pointer that tells us where is the next minimum. So once we inserted values inside the heap, we don't worry about shifting them. Okay? So it turns out actually to be a great idea because, as I mentioned, heaps are very popular in many applications, including network applications, including embedded systems, and over there the memory is limited. So if you are given a choice, if you're an embedded systems developer, between a heap implementation that is a tree and a heap implementation that is an array, of course you will pick the array because the array will take less memory and it's faster to work with in an embedded context as well. So this is why heaps are popular actually, because they are implemented as arrays. Now, there's also something I'd like to tell you, that because of the way heaps are structured, we can merge two heaps very fast, which enable us to do a lot of interesting stuff. So if we're given two heaps and some key k, we can create a new heap with the root node, storing this k value, okay, and the two sub heaps as subtrees. And then what we do next is we will do down heap to restore the heap order property. Okay, so I could easily merge any two heaps with given a new value that I would like to insert it in them together. Okay, in the new heap. That's what you see here. I got one heap that 3, 8, and 5, another heap 2, 4, and 6. Okay, if I would like to insert or merge them together, I will just wait for the new entry. Let's say it's 7, so I put it as the root of both of them, and then I down heap it. Okay, when I down heap it, what we'll end up with is also a heap. And this is an important thing, because the first one alone, the 3, 8, 5 was a heap, 2, 4, 6 was a heap, but the merging of the two might not necessarily be a heap. When I get a value, when I down heap it, both of them again will be a heap. What we can also do with a heap is that we can easily construct a heap from any given sequence of entries or values that are not sorted according to the heap order property, and we can do that in a log n phases. So let's see an example of what I'm describing here. Let's say you're given the sequence 16 to 10 that appears at the top of the screen, and you would like to create a heap from it. Now, what you will do is you will count the number of entries and divide by 2 to get the number of values that you will put at the leaf level, and you go and put them at the leaf level. That's what you see in the first three in this slide. The 16, 15, 4, 12, 6, 9, 23, and 30 are all coming from the list of numbers without any modification. Now, from now on, I have to worry about the heap order property. So once I see a new value like the 25 that comes afterward, I will still put it at the parent of 16 and 15, and the 5 will be the parent of 4 and 12, 11 will be the parent of 6 and 9, 27 will be the parent of 20, 30, 23 and 30. but I can't just do that and stop, because I could have a violation of the heap order property. So what I'm going to do is I'm going to check the new entered value, the 25, 5, 11, and 27, according in comparison to their children. I would like always to have the smallest value up and the larger values down. So if you look at 25, 16, and 15, I need to bring the 15 up and then the 25 down to the right, because that will make it 15 the parent, and it will have children 16 and 25. And we said as long as the children are greater than or equal to the parent, we are happy with, in the case of the min heap situation. The same thing for the 5, 4, and 12. I need to bring the 4 up and the 5 and 12 down. It will be its children. For 6, 11, and 9, I will have 6 up and 11 and 9 will be its children. 23, 27, and 30, I will have the 23 up, and then and 27 and 30 will be its children. What you see at the top 3 here is the insertion of the values without the heap down implementation, and what you see at the bottom 3 is the implementation I was referring to, or the consequence of the change. The 15 becoming the parent in the leftmost subtree, and then the 4 becoming the parent, the 6 becoming the parent, the 23 becoming the parent. Now, I will move on to add more elements from the array. So I add the 7 and the 8, and I will do the same thing again. I will compare with the children and propagate the smallest of the two. So I will propagate the 4 upward instead of the 7, and then I will down heap the 7 all the way till at the leaf level, because 5 is less than the 7. So I down heap the 7 with the 5, taking exchanging the places. The same thing for the 8. I will down heap it with the 6, okay, bringing the 6 upward, and then that will stop there. And finally, I insert the last element in my given sequence of values, which is the 10, and again I down heap it, bringing the 4 up, and then exchanging the 10 with the 5 and the 7 to bring it all the way down. Okay, so this is called a bottom-up heap construction, and it's actually done quite nicely in log n, because I'm always working with the smallest value, which means I'm ignoring the right side and working with the left, or working with the left side and working with the right side and ignoring the left. I've mentioned already a number of heap usages. So the top usage, of course, is to implement priority queues. Okay, it could also, by the way, use to extract the case smallest or largest element in an array, whether you use min heap or max heap. So of course, in the max heap situation, we would reverse our heap order property. So the largest value would be at the root, and the rest are smaller than it. Now level by level all the way till the leaf level. So I could use that to find the case smallest largest element, and we also use it in the Dijkstra algorithm, which you have seen in the tutorials. So you could also use it in that context when you're finding the shortest path. Now this is also a very common heap interview question. That's why I'm covering it here. By this we finished the course. I was planning to cover other material, however, due to a shortage of time and the need to post these videos to the university network, I will leave the rest of the material for you, but you're not responsible for them for the purpose of the assessments at all. So what you will need to do is just study the material up till this point in the videos, and the links included in the following slide will not be a part of the course content except for the heap. This is the references for today's lecture. I've covered heaps in detail. I'm giving you a reference for it, but I will not cover segment trees or graphs for this offering of the course. Consequently, this is optional material. You will see some tutorial related material to it as well, but again, this is not covered in your assessment, and you're not responsible for it. I'm talking about segment trees and graphs.